Welcome to our webinar Selectivity in Line Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I am happy to guide you through this second session of the webinar. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I am part of Siemens Power Academy in Nuremberg as a certified trainer for protection. And today, I am introducing you to the Selectivity in Line Protection lectures. How selectivity works in overcurrent protection, how selectivity works in directional overcurrent protection. And since we receive one question rather often, yes, we will record the webinar and make the recording and the slides available to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your questions during the dedicated Q&A session after the series on 21st of June. In addition to me reading aloud your questions, you could also chat with our experts in the background. Please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now let me introduce our expert, Professor Dr. Siegfried Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH Aachen University. He joined Siemens in 1986. For many years, he was head of the product lifecycle management for protection, where he was deeply involved in the design of CPROTEC 4 and CPROTEC 5 relay families. Within the Master Course of Power Engineering at Brandenburg University of Technology, Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens but continued his university lectures. Siegfried, the stage is yours.
In this video I would like to talk about selectivity in line protection. Remember, what is selectivity? If we have a short circuit somewhere in the network, the short circuit current is flowing through different ways to the short circuit location. That means in our network several relays will see the fault current, and selectivity means that only the relay of the affected line or transformer has to trip. The other relays will also see short circuit current, but they should not trip because their devices are carrying the short circuit current but have no short circuit. And this has to be dealt with in a different way for our 3 different short circuit detection functions: differential protection, distance protection, overcurrent protection. For differential protection is pretty easy because this principle is by itself selective. That means this reacts only if there is a fault on a protected device. That means in the context of selectivity, that is pretty easy. If we look at distance protection, on the first glance, it looks also pretty simple because distance protection measures the impedance, and by this it can decide, is the short circuit on the own line or cable, or is it on the next line? But we will see later on, it's not that easy. We also have to look into that. For overcurrent protection, and that is the topic I would like to start with, There the situation is the protection relay only sees the current. That means it only sees there is a short circuit, but deciding is it on my line or is it somewhere else is not so easy, and for that reason I would like to start with discussion about selectivity in overcurrent protection. Remember, overcurrent protection relays have a structure which is shown on the left side of this slide. We measure the current in the three phases, and this goes into the protection relay. We do some analog to digital conversion. That means we measure then the current values, and then we have these green blocks which make a decision if the current value is above a certain limit, it may trip or not. Additionally, we also measure the earth current. That is can be a separate measurement input, or it can be calculated internally. We give that to this yellow block, and also there we have a certain characteristic. And if this yellow block decides to trip, we will also give a trip command. Remember then, in the right bottom corner, I show these diagrams about the setting. We always have to consider there's a certain range of current which we see in normal operation. For the phase current, it's from 0 to a maximum load current. For the earth current, it's a very small value. And then we have the range of short circuit currents, which is indicated in red color here. And we normally have a setting value somewhere between the red and the green area. And selectivity is, first of all, about how to define this value, and the second parameter we can influence is we can think about time delays. That means if we are above that limit, what is a proper time delay? Please remember also the area of application for overcurrent protection is distribution, where we normally have radial systems. That means systems of the type I show in the right upper area of this slide. You often have one substation where you feed the whole network, and then from this substation you have radial feeders. That means you have no meshes there, because the feeders just end at an open connection point. So now the question is, how can we achieve selectivity in such a system? And actually there are two or three options. We can make a so-called discrimination by time, we can make a discrimination by current, or we can combine both of these. So let's start with the first one, discrimination by time. If we look into these blocks in the structure of the overcurrent relay, that means these green blocks where you have as an input quantity the current, and as an output quantity you get a trip signal depending on the size of the current, on the amount of the current, and with a time delay. And we assume now we have this type of characteristic, which is called definite time overcurrent protection. That means you have a characteristic with a setting value I greater, and as soon as the measured current is above this value, we will start a timer, and after this timer that has a settable value, after this timer is elapsed and the current is still there, we will then issue a trip command. And it's called definite time because this time delay is independent on the size of the current. If the current is above this value, the time delay is always the same. So how does this look like? What I show here is one feeder of our distribution system. You see on the left side the infeed. That means all short circuit current comes from the left side. And then you see several lines or cables. And at the beginning of every line or cable, we have a circuit breaker with a protection relay. And if we assume that we have a system, for instance, a cable system here with relatively short cables, the short circuit current does not vary significantly along the line. That means whether we have a short circuit on cable 2 or cable 3 or cable 4, the short circuit current is nearly the same. And then on these intermediate stations, B, C, D, and E, we have transformers who do the step down into low voltage networks. Now let us assume we have a fault somewhere on this feeder. We assume we have a fault on cable 3, short circuit on cable 3. Now the short circuit current comes from the left side. That means relays, the first 3 relays at locations A, B, and C, see fault current. But the only thing they see is the fault current. And from the amount of the fault current, they cannot decide where the fault is. They only see the fault current is high enough that we consider this as a short circuit. And which one should trip? Only the relay at location at the bus bar C should trip, because cable number 3 is the cable with the short circuit. The protection relays at substation A and B should not trip in this case. The protection relay in substation D will also not trip. In this case, it doesn't see any fault current, so it's not affected by the whole story. So how can we get the selectivity? And the simple solution in this case is we make different timer settings. That means the rightmost relay gets the lowest timer setting, in this case 0 milliseconds. And this in this example, I made settings. Next relay gets 300 milliseconds, next one 600, and the one at the in-feeding station gets 900 milliseconds. That means you see in this case I have a difference in time delay of 300 milliseconds. That's pretty much. You can also make it a little bit smaller. But first of all, we look what is now going to happen. The short circuit starts. Our 3 relays see the current is above the limit. They start their timer. And in the relay at substation C, the timer will expire first after 300 milliseconds. Then this relay will trip, will open the breaker, and then the current flow stops. That means in the other 2 relays on the left-hand side, the timer will reset before the time delay of 600 or 900 milliseconds is reached. That means these 2 relays will not trip the breaker. That means by this simple arrangement, we get selectivity. The right relay at substation C trips the short circuit. So selectivity is there. Advantage is that is a very simple logic. The disadvantage is, and that is a significant disadvantage, we have pretty high fault clearing times near the infeed. Imagine we have a short circuit on cable number 1. Then only the relay at substation A sees the fault, but it doesn't know that it is on its own line. It just waits for 900 milliseconds until it trips. It is still selective, but it's a long time delay. 900 millisecond short circuit current is a long time, and it's a critical thing. That means normally we should make the time delays as short as possible. Now, of course, you could ask the question, but why do we make these differences, 0, 300, 600, 900? Couldn't we make it smaller, 0, 1 millisecond, 2 milliseconds, 3 milliseconds. Wouldn't that be a possibility? Because the time measurement in a microprocessor relay is not an issue. That means we should look a little bit into that situation and figure out what is the minimum difference in timer setting we need so that the whole story works. And to understand that, we look a little bit into the timer. In this case, imagine we had a short circuit on line number 3, and we will now look what is going to happen in relays at substation B and C a bit more in detail, and that is shown in this slide. You see on the upper trace we have the short circuit current. To the right we have the time axis. Then we see current is flowing, and then on the 2 traces below that we see what is going to happen in the 2 relays. First of all, both relays need some time to detect the fault. No, internally we have algorithms, they need some data windows to calculate the current, so they need some time to detect the fault. If the relays are identical and the setting is identical, these delay times will be the same. If the relays are of totally different type, for instance, one is a digital relay, one is an electromechanical relays, these time to detect the fault can be pretty much different. Then both relays start the timer. You see here the timers of both relays. Relay number 1 in this case has the shorter timer setting, and after some time this timer setting elapsed, it issues a trip command, and now the point is the trip command goes to the circuit breaker, but the circuit breaker doesn't react at once. The circuit breaker needs some time to open because there's mechanical things have to move, and finally the short circuit current can only be interrupted at the 0 crossing. That means from the point where the timer has elapsed to the point where the current is really gone, we have some time. And that time depends on the breaker, and that is unfortunately a time which is not very well known. It depends on the maintenance state of breaker and the type of the breaker and so on. And we must be careful that, remember, relay 2 is expected not to trip. And then after the fault has gone, relay 2 needs some time to detect that the fault has gone. That's the so-called reset time. Again, that depends on the algorithms, on the data window of the algorithms. So we must be careful that the timer of relay 2 does not elapse before the reset time is over. That means the time difference between the timers of the 2 relays must be at least the time of the circuit breaker plus the reset time, plus maybe some differences in the fault detection time at the beginning. And normally protection engineers are pretty much careful, so on the right hand side we add some margin to that. And if we have something in the range of 40 to 60, 70, 80 milliseconds for the circuit breaker, maybe 20 milliseconds for the reset time, then there are some other reasons to have significant margin there. And with this calculation you end up in required differences of the timer setting in the range of 200, 250, 300 milliseconds. You should not go below that. In my example I took 300 milliseconds. It's more the upper end. I think nowadays you can also go down to 250 or even to 200, but you must be pretty much careful then. Okay, that was the difference in timing. You can display this arrangement of different timer settings in this so-called grading diagram. You see here on the top of the slide again our arrangement we had with the different timer settings, and in the lower part I show the so-called grading diagram. It shows the tripping time we will have depending on the location. That means from left to right you see the distance from the infeeding substation, and if you go to the rightmost area you see if you have a fault there it will be tripped in 0 milliseconds, the red line, because the last relay has a time delay of 0 milliseconds. And what you can also see, we have a backup included. That means if this relay doesn't work, or if the breaker doesn't work, a fault on the rightmost cable will then be tripped by the orange relay with a delay of 300 milliseconds. It will be a little bit reduced selectivity there, because we trip a bit more than we should, but we have a backup. And in this case you can even say we have a backup for the backup and even another backup for that. That means here we are pretty safe that somebody will clear the fault. If you go more to the left, you see if we look at the second cable from the right, it will normally be tripped in 300 milliseconds by the orange relay. If the orange relay fails, the purple relay will be the backup. That means the nice thing in these type of grading is you have automatically a backup included. You must be careful. In this case there's one exception. If we look at the cable on the left side, if we have a fault there, one not so nice thing is the tripping time is pretty long. It's 900 milliseconds. And in this case, we don't have a backup. That means for this particular cable, if we want to have really a complete protection system, we again have to think about other relays taking over the backup in this case. So this was the principle just of discrimination by time, mainly applied when we don't get information from the current. I said we assume here in this case we have a cable system, for instance short cables, where there is no big difference in short circuit current. The second possibility we have, that are cases where we can get information from the current. And I can show you an example for that. Look at this system. We have here again a distribution system, but in this context I would like to discuss it including the transformer. That means we have on the right side the same arrangement that we already discussed before. We have different relays, we can make the timer setting there, and we now discuss the relay at location A. And now I would like to consider three locations for short circuit current, number 1, 2 and 3. And in this case I did a calculation of the short circuit current for the three locations. In this case I also assumed we don't have a network with short cables. In this case I assume between substation B and C, I assume a 30-kilometer overhead line. And if you now do a calculation of fault current, first of all at location at location 1, that means a short circuit on the high voltage side of the transformer. In this case it was 25 kiloamp short circuit current seen by relay A. Relays B and C will in this case not see any short circuit current. If I have a fault at location number 2, then relay number 1, relay A will see only 2.4 kiloamp. Relay number 2, that is the distribution side. Of course, there we have higher currents because the voltage is lower, sees 13 kiloamps, and the relay at location C doesn't see anything. If we have a fault at the very end of the whole story, relay at location A sees only 70 amps, relay at location 2 sees only 4 kiloamp, and the last relay C also see 0.4 kiloamp. And that means in this case, for instance, relay number at location A can take information from the current. It knows if I have a short circuit at location 2, the maximum current I will see is 13 kiloamp. That means if relay A sees a current of more than 13 kiloamp, it knows this cannot be somewhere downstream. This must be on the high voltage side of the transformer. And for that reason, it can take this information as a base for a fast trip. The same thing applies to relays at location B. If they see a current above 400 amps, it knows the fault must be somewhere on the line, because if the fault is at location 3, it must be lower. That means in such an arrangement where we have significant impedances, here it is the transformer and the long line, if we have significant impedances involved, we can use the current to decide, do we need a fast trip or not. So we had discrimination by time, discrimination by current. We can compare these. Discrimination by time is a very simple thing. We can always apply it. It has simple setting. We just have to adjust the timers. But the disadvantage is we end up with high tripping times near the infeed. Discrimination by current. With that we can avoid long tripping times in certain cases. But this requires significant impedances between the relays. And for that reason, in real life, both methods are normally somehow combined, and I will show 2 examples of how we can combine discrimination by current and discrimination by time. Let's start with a 2-stage definite time overcurrent protection. What is that? That is a characteristic which is a little bit more complicated, but which is standard for definite time overcurrent relays. In this case, we have 2 settings for the current and also 2 timer settings. We have one current setting I greater with a timer setting assigned to that. That means if the current is below this I greater setting, the relay will not trip at all. If the current is above this setting I greater, it will trip with a relatively long trip time. And then if the current exceeds a certain setting value I greater, it will then trip with a much shorter tripping time. So that is a characteristic which is called 2-stage definite time overcurrent protection, which is available in all definite time overcurrent relays. What can we do with that? Let's look again at that example I already showed before. We have here this feeder. We have an overcurrent relay on the high voltage side of the feeder, and on the medium voltage side we have different cables feeding the city, different substations in the city. We can now imagine on the distribution side, we again do this grading concept. We start somewhere with 0, In this case here, we have the 300 milliseconds in the orange case. We have the 600 milliseconds in this relay. And now we could say, okay, we take the 900 milliseconds for the leftmost relay, which would then look at short circuits on the bus bar, and which would also serve as a backup for the downstream relays. And now we can take the current as a criterion and can say if this relay on the right, on the left side sees a current which is high enough, it knows that is not a short circuit on the medium voltage side of the transformer. It must be a short circuit on the high voltage side, and there is no need for a long time delay. And then it can trip faults on the high voltage side of a transformer without time delay. That means we must do short circuit calculations for the system and then make the timer setting in an adjusted way. That is a thing what you often find in connection with transformers. Another possibility is the use of so-called inverse time overcurrent protection. In this context, you don't have this stepped characteristic. You have these curves as trip times. That means in this diagram you have on the horizontal axis the current, on the vertical axis you have the time delay, and there you see you have trip time curves. Again, you have one current value. If the current is below that value, you will not have any trip. And if the current is above your setting value, that means we have again a setting value of the current, like indefinite time overcurrent. But the difference is if the current is above the setting value, the delay time depends on the current. And what I indicated in this diagram is there are different curves in use. And if you look at this strange equation below the diagram, you may ask yourself, where does this strange equation come from? Is there a big theory behind that? The answer is no, there is no big theory behind that. The reason where we have these curves is the following one. This concept was started in very early times where protection relays were still electromechanical relays. That means at that time overcurrent relays were built with induction discs, and people made a mechanical construction where the characteristic was more or less determined by these induction discs. And then these things were brought into the market and they had a certain characteristic. And these characteristics were standardized in the early days in different countries. At that time we still had national standards. So there were US standards, there were British standards, there were German standards and whatever. So all countries more or less had their own standards. And in the meantime, the whole story has been globally standardized. That's an IEC standard. But of course, this IEC standard had somehow to show what was already there before. That means what came from these electromechanical relays. That means what people in this committee did is they measured the curves from the electromechanical relays which were in operation, and then they did a curve fitting. That means they defined equations which lead to a curve which are pretty much similar to these electromechanical curves, and that is why we end up in such strange equations. You also have different shapes, you see that? That means there are different equations available. Sometimes they have names like inverse time, very inverse, extremely inverse. I think in the standard, in the meantime, they are just, we have just assigned numbers to that. You also find these plots either with linear scale or with logarithmic scale. That means you must always be a little bit careful what type of scaling you have. And they, of course, you can imagine in digital relays, you just program this characteristic. It's not a big thing. For us, the question is, how can we use this type of characteristic to achieve shorter tripping times near the infeed? That means to compensate a little bit the problem we have with definite time overcurrent relays, that the tripping times near the infeed are pretty long. And to illustrate how that works, I would like to show this example. You see here again a feeder, in this case with 3 overhead lines. In this case, it are really overhead lines. I did a calculation with 5 kilometer, pretty weak overhead line. And again, here I did a short circuit calculation. That means for the 4 different fault locations in this picture, I calculated the short circuit currents, all relays C. You see, you end up in a sort of a matrix. And you can see here already that the short circuit current significantly depends on where the fault is. That means in this arrangement where we have an overhead line with significant impedances, we can get information from the current. For instance, look at relay A. If that has a close-in fault, it sees a short circuit current of more than 14 kiloamps. If the fault is beyond the next substation, it's only 2 kiloamps. If it is beyond substation C, it's only 1 kiloamp. You see, in this arrangement, there is information in the fault. And then for this arrangement, I included now these inverse time characteristic. That means for all the relays, I made a setting for the inverse time characteristic. And then if I draw again the grading diagram, as we did it before for the definite time overcurrent relays, it looks like this. You see here, if you have a fault at the end, on the horizontal axis, you again have the distance along our arrangement, 15 kilometer. And the vertical axis again is the tripping time. You see here, if we have a fault at the end of the arrangement, the green relay will trip with a certain delay. As a backup, we have the red relay. If we have a fault somewhere on the middle, the red relay will trip with a delay. But the important thing is, if we have a fault at the infeed, near the infeed, you see here that will be tripped by the blue curve, but there the tripping time is now reduced in comparison to the application of the definite time overcurrent, because we use here the inverse time characteristic. Of course, if we do the grading in this context, we have to consider some rules. Again, we must look at the backup. That means for all fault locations, we must be sure that at least 2 relays should pick up. That means the relay which is expected to trip should see the fault, but another relay which is expected to serve as a backup should also pick up and start its timer. It should not trip normally, but it should pick up. Selectivity must be guaranteed. That means we must also observe a certain timing distance between the curves. Remember what we discussed for the definite time overcurrent relay setting, that we need this 200, 250, 300 millisecond time difference. That means here we must set the curves in a way that they have a proper difference. Otherwise we get conflicts and we get non-selective tripping. And the last issue, which is also clear, we must not pick up with load current. That means the current setting values of the relays must be high enough that we don't pick up with load current, even not in critical situations. Remember, I discussed that example in one of the first videos where you had somehow a blackout of a part of a city which has been without energy for some hours. If you re-energize that, maybe a lot of aircons will be starting then, which have a pretty high current, and your setting should be high enough to avoid tripping with that current. And you can imagine this looks pretty much simple if you are dealing with 3 relays, but if you are dealing with a big network with 100 relays, it becomes complicated. You must do network calculation, short circuit calculation, load flow calculation, and for that reason this calculation of setting values following these principles is normally done with grading programs. Within Siemens we use the program SYNCAL. You can use this program to do network calculations, but you can use this program also to do the grading of overcurrent relays. You see here the output, input and output of such a program run. On the left-hand side you see the input, that means the topology of the network with transformers, with protection relays and so on. And then on the left-hand side you see the result. You see here the grading curves of the different relays. In this case, that is a combination of definite time and inverse time relays. You see here some stepped characteristics, and you also see some inverse time characteristic. That was a short look into grading of overcurrent relays. In the next video, I will have a short look on what can we do with directional overcurrent relays. Let's have a look at selectivity in conjunction with directional overcurrent protection. The concepts we discussed in the previous video, how to get selectivity with overcurrent protection, will work only with radial systems. That means we should not have any meshes, and the infeed has to come from one side. As soon as we have infeed from both sides, you can easily check these concepts will not work. What we often have in distribution systems is basically a radial systems, but with some exceptions. Like shown in this example, we have 2 parallel lines. That is a mesh. Theoretically, is no longer a radial system. It's a mesh system because they are on one location 2 cables or 2 lines in parallel. Or sometimes you also have things like that. You have a feeder, but you have infeeds from both ends. That is also a thing which sometimes has to be considered in conjunction with the conversion of our systems, where we implement more and more renewables. With that, you can also end up in a situation that you had a radial system with infeed from one side, and now you install renewables. You have to think about, does that affect your protection system somehow? What can we do in these situations? Of course, you can apply distance protection to overcome that situation, but there is an easier solution for that. And this easier solution is using directional overcurrent protection in these particular cases. Now the first question is, what is directional overcurrent protection? you could say is simple. It measures the direction of the current. But remember, we have AC, and in AC the direction of the current changes 100 times or 120 times per second. So what is the direction? If we talk about the direction of the current, we measure the phase angle between the current and the voltage. And if that is within a certain range, we say the current is forward. And if that is outside this range, we say the current flow is reverse. That means a directional overcurrent relay has a voltage input. That means in terms of relay hardware, it's a little bit more. You need some software behind that. But you also need in your substation a voltage transformer, because you must measure the voltage of your line or your cable. That is required, whereas if you have a normal overcurrent application, it's not necessary. Then I should mention the definition of direction is normally as follows. If we see a short circuit current flow from the protection relay into the line, we define that as forward. Opposite direction is called reverse. So what can we do, for instance, in this case of two parallel cables with a directional overcurrent relay? Let's look at this arrangement again. On the top we have the infeeding bus, and then we have the two cables feeding the bus on the lower side, and then from there we go with radial feeders into our system. And now we assume we have a short circuit on one of the cables. Important thing, of course, is if we have a fault on one cable, we have to trip this cable, but of course the other cable, the parallel cable, should remain in operation. Otherwise it doesn't make sense to have two cables in parallel. So what's going to happen if we have this short circuit there at that location? We have a current flow, and this shows a little bit the current flow. We have from the infeed current flow directly to the short circuit location, but we also have current flow via the parallel cable and then coming to the short circuit location from the other side. And the share of the two current flows depends on the location. If the location is very close to the infeed, majority of current comes on the direct way. If the short circuit is near the lower bus bar, it's nearly 50-50. That means in this case, all four relays in our parallel cable systems will see fault current, and they will all pick up first of all. That means relay 1, 2, 3, 4 will pick up. And then we have here these two relays on the lower ends, which are a little bit gray color. They are directional relays. That means they have a preferred setting, and this setting is indicated with the red arrow in the relay box. That means they will react only if the current flow is in line with the setting. And if you look at the bottom right relay, there the current flow is opposite to the direction of the arrow. That means this relay says, I'm a directional relay, I will not react on current flow in this direction. That means that relay number 4 will block the timer. And relay number 3 sees a current flow according to the setting, and it can react on that. And in this relay, it doesn't make sense to have any timer setting, because if this relay sees a current flow in this direction, it must be this situation that there is a short circuit on that line. That means it can trip at once. The two green relays on the top will also, that are normal overcurrent relays, they will also start their timers In this case, I have 300 milliseconds. What is going to happen then? Relay number 3 trips undelayed, opens the breaker, and after the breaker is opened, this current flow through the parallel line to the short circuit location is interrupted. And that also means that in relay number 2, which also started the timer will reset because the current flow is suddenly gone. And then we wait until the timer setting of relay number 1, until the timer is elapsed after 300 milliseconds. Relay number 1 will trip the circuit breaker. Then the current flow will stop. And that means we have cleared the fault and the parallel line, the line on the right side or the cable on the right side, is still in operation. So you see, with the directional overcurrent relay, you can make a proper protection even in such case where you have 2 parallel cables, which is theoretically a mesh system. The second possible application of that is shown here. That is also a distribution feeder. And in this case, we have in-feed from both sides. And to end up in a selective protection scheme, you also have to apply directional overcurrent relays on nearly all locations except the 2 outer sides. And again, here we can make this example, a short circuit on the left cable. Short circuit current comes from both sides. All relays will see the short circuit current. Some of the relays will block because the short circuit current is opposite to their setting. And then relay number 2 will trip, in this case undelayed. You see, if the short circuit would be on the center cable, we would have a little bit of delayed trip. After relay number 2 trips, breaker opens, short circuit current from the right side disappears, and then we wait until the timer of the leftmost relay has elapsed, and then it trips and the current disappears as well. So that were 2 examples with directional overcurrent relays. They can be applied if you have basically a radial system with a few exceptions. It's easy to get selectivity then.
Thank you, Siegfried. That has been an interesting session. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on 21st of June. If questions come into your mind later or you would like to go for more details, please visit our trainings platform at Siemens Power Academy. I'm sure you will find the right information and training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through this first session on selectivity in line protection. In this session, we learned how selectivity works in overcurrent protection, how selectivity works in directional overcurrent protection. I'm looking forward to meeting you soon in the next session of selectivity in line protection on June 13th, with focusing on how selectivity works in distance protection. Stay safe and sound. Take care and goodbye.